And now we discuss the mechanical energies. So we have the mechanical energy. So in the mechanical energies, we have two types of energies. We have the kinetic energy, and then we have the potential energy. So potential energy. So the kinetic energy is defined so that whenever a body is moving, it will have the kinetic energy. So the kinetic energy is the energy that is because of the motion of the body. If anything is moving with some velocity, it will have the kinetic energy. So mathematically, it is defined as 1 by 2 mv squared. So we can see here, whenever something is moving with some velocity, so it will have some kinetic energy. So if we have, for example, if it is directly proportional to the mass of the object. If we have the mass is higher, the kinetic energy will be higher. If the mass is smaller, the kinetic energy will be smaller. Similarly, it is proportional to the square of the velocity. So if the velocity is higher, we will have high kinetic energy, and if the velocity is small, we will have the small kinetic energy. Similarly, if anything that is moving, so we have, for example, moving cars, we have moving horses, we have running person, for example, we have anything that is moving, it will have some kinetic energy. Similarly, we have the potential energy. Potential energy is defined as mgh. Potential energy is actually existing in the conservative fields. We will just in the coming lecture, we will also discuss the conservative fields. For example, the gravitational field is the conservative fields. So in the conservative field, if something is changing its position, for example, it will have the potential energy. So it's kind of a stored energy. So if I have a block, for example, here on the ground, if I lift it to this position here, and the height is h. So the height is h. So I have the mass. So this is a mass. So I lift the same mass to some other position in the gravitational field, I will have some potential energy. So this potential energy is stored in this object here because of its position. So this potential energy is actually due to its position. So why? Because if I let it go, the object will come towards the surface of the earth. So this potential energy will be converted to the kinetic energy. So it is the one form of the type of the mechanical energy. So we have two types of mechanical energy. One is the kinetic energy, and another one is the potential energy. And now we discuss the work energy theorem. So we have the work energy theorem, or it's also known as the principle, the work energy principle. So we just discussed about the work done. The unit of the work done was joule, and the energy also has a unit of joule. So this has a unit joule, and this has the unit joule. And now we want to know what is the actually relationship between the work done and these mechanical energies. So for that, since we want to know what is the relationship between the work done and these mechanical energies, and for the mechanical energy, we can see here we have the velocity. So something is moving. So we have the velocity involved, and we have the displacement involved. For example, we have the height, or in the work done, we also have the displacement. So for this purpose, we will use the equation of motion that we calculated long time ago in our lectures. So we will use the second equation of motion. So we have the equation of motion, So it's the same thing that we already discussed. I will just write this equation of motion. So we have the 2a displacement equals the final velocity and the initial velocity. So I will not derive this right now because we have already derived this in our previous lectures. So we can also write, so we will rearrange this equation here. So we will bring this 2a to the other side. We will have 1 over 2a multiplied by the Vf minus Vi squared. And now what we do, so this is the equation number A, and we have, for example, F equals ma. So this is equation number B. So what we do, we multiply this equation number B with the A. So what we get is the force. So the force multiplied by displacement, we just multiplied, and then we have the ma. So we have the ma. So we multiply the force on both sides. So we have the, that doesn't change anything, because on the both sides, so we can cancel these two, so it will not change anything. So, and then we write the same equation here, which is 1 by 2a Vf squared Vi squared. And now we cancel these two here. So what do we see here? So we have, for example, we have the force multiplied by displacement, and we just discussed that the force multiplied by the displacement is the work done. So we can write work done here instead of this term. And now we rearrange this term. So we have the work done, so we write work done for these two, and then we rearrange this here. So we have the 1 by 2m. So we just remove this bracket, and then we will rewrite. We have the m here, we have the 2 here, so the a is cancelled. So we write 1 by 2m Vf squared minus 1 by 2 mvi squared. So what do we see here? So we see here that we have the this is the, if we look at the formula for the kinetic energy, we have the 1 by 2 mv squared, and here we also have 1 by 2 mvf squared, 1 by 2 vi squared. So what does that mean? It means that, so we have the difference between the final kinetic energy and the initial kinetic energy. So we can write, so work done is equal to kinetic energy final F kinetic energy initial. So this is the work energy theorem. So now we have the relationship between the kinetic energies and the work done. And now we want to understand. So it means that whenever we have something is moving with some kinetic energy, and the kinetic energy changes after some time, whether it's either it increases or decreases doesn't matter. But if the kinetic energy of a system is changed, then we will have some work done. If the body is moving with the same kinetic energy and does not change, that means that the final kinetic energy and the initial kinetic energy will be the same. So this difference will be 0. It means that no work is done on the system. So if the kinetic energy is changed, we will have some work done. It means that some force is applied, and then it actually changes the kinetic energy of the system. And now we will discuss a related example. So I related example. So a person lifts an object from point A to point B. So we have here an object which has some mass. Initially its velocity Vi is 0, and finally some person lifts this object to this is point A and we have point B. So a person lifts this mass from point A to point B. So initially the velocity was 0 and finally the velocity is also 0. And this is the height. So we want to know what is the work done according to this work energy theorem. So we have two work done. So one work done is done by the person. So the person has done some work, and that work is what he did was lift this object from here to here. So this is some displacement is covered, and we also have some force that is involved. So we can write mgh, and now the work done by the gravity. So it will have minus sign because the person has applied a force in this direction, which is upward, and the gravity is applying a force in opposite direction. So we will have the work done, which is negative. So we want to know what is the total work done. So the total work done is 0. Why? Because first of all we have the two work dones are in the opposite direction. Another thing that we notice is that the velocity here, the initial velocity is 0 and the final velocity is 0. So first thing that we see is that the work done by the person is mgh, and the work done by the gravity is minus mgh. So they are in the opposite direction, so they will cancel each other and we will have the 0 work done. So of course individually the work done by the person is not 0 and the work done by the gravity is not 0, but the total work done is 0. And the other thing that we see is that the initial velocity is 0. That means the initial kinetic energy is 0 here, and the final velocity is 0. That means that the final kinetic energy is 0. So 0 minus 0 is 0 work done. So that's how we define the work in this case. And now we discuss another example. So the example is that a body is thrown upwards with some initial velocity, and gravity acts on this object and it stops at some point, and we are asked to find what will be the height of this object. So first we need to understand. So initially this is a body, and from point A, for example, we have this is the ground level, and somebody give initial velocity to this object. So this object has some initial velocity. So somebody throws an object in opposite direction, and the gravity, so mg, is acting in the opposite direction. If the force is applying in opposite direction of the initial velocity, so at some point this object will stop, and the final velocity at some point, so this is point B, and so point B, so Vf is 0. So the Vf is 0. So we are asked to find out what is this height. If you remember, so we have calculated, actually we have solved this problem when we were talking about the projectile motion. So when we threw something up with some initial velocity at the 90 degrees, we calculated the height using the concept of projectile motion, but here we will use the concept of the work energy theorem and we will get the same answer. So we will see. So the work energy theorem tells us that the work done is equal to the kinetic energy at point B minus the final position is here, which is B, and then we have the A. So the kinetic energy at point A. So the kinetic energy at point B is 0 because the final velocity is 0. So the initial velocity was not 0, and at some point, due to the gravitational force in opposite direction, the final velocity is 0 at this point, point B. So the kinetic energy at point B is 0. So now what is left is kinetic energy at point B. Similarly, we have the work done by the gravity is minus mgh. We have the minus mgh, we just saw it there in the other example, and we can write minus 1 by 2 mva square, and this way va is the initial velocity. So minus minus cancel each other, and then we have the mass cancels, and then we have the height, and this g comes to the other side. So we will have the initial velocity, which is also va squared divided by 2g. So we got the same answer what we got when we calculated this height using the concept of the projectile motion, and now we just use the work energy theorem and we calculated it again, and we found out that we get the same result.